Recording. Now I'm recording. Okay, good. Okay, fantastic. Okay. Okay, so last lesson, we, at the end of the lesson, I assigned homework 6. Okay, so let's go over homework 6. Okay, so this is homework 6. Does anyone have any questions about particular problems from homework 6? Anyone have any questions? Okay, so if there's no questions, then actually, so I'm just going to go over one or two myself. So let's look at 5.4 number 1. So 5.4 number 1, let x be a continuous random variable with probability density function. F of x equals 2/3 x for x between 0 and 1 and 2, and find these probabilities, right? 5.4 right here, right? Okay, so let's do this one. Let's find this probability. Okay, so f of x is this function, and we want to find this one. So let's just. Okay. I'm going to mute everyone's mic. Okay. So homework 6. This was 5.4, number 1 on the homework. Okay, and so the question is to find the probability that x is at most 1.2. Okay, so this probability is equal to the definite integral from 1 to 1.2. So it's equal to definite integral from 1 to 1.2 of the function 2/3 x dx. Okay, and so you could calculate that, and so you get 1/3 x squared as an antiderivative, and so you evaluate that from 1 to 1.2, and so you just get 1/3, and then you subtract. So the value of 1.2 squared, 1.2 squared minus 1 squared, and that's equal to, so it's 1.44 minus 1. That's 0.44 over 3. And so 0.44 over 3 is 0.146. Okay. Okay. And so that's the probability x less or equal to 1 from that problem. Okay. Oh, sorry, I'm recording this time. Okay. So, all right. So if there's no question with the homework, let's keep going. So at the end of last class, okay. So last class we ended with okay. So last class we ended with example 5.8. Which is weird. Okay, we went further ahead than I thought. Okay, so so we're done with, oh wow, done with 5.6. That was very easy to know. Okay, so let's start 5.7. Okay, so 5.7.1 is on the continuous uniform distribution. Okay, so a continuous random variable x has a uniform distribution. And is called a continuous uniform random variable if its probability density function can be defined as follows. Okay, so definition. Okay, definition 5.3. Let alpha and beta be constants with alpha strictly less than beta. The function f of x is equal to it's equal to 1 over beta minus alpha for alpha less than x less than beta, 0 elsewhere, is the uniform probability density function. Okay, so let alpha and beta be constants with alpha less than beta. The function f of x here is called the uniform probability density function. Okay, so that's the uniform probability density function. So the characteristics of a continuous uniform random variable capital X are the following. 1, the possible values of the random variable are restricted to some interval alpha comma beta of real numbers. 2, if I1 and I2 are subintervals of alpha comma beta of equal length, the probability capital X takes on values in either is the same. Okay, so we have this uniform probability density function, and there's 2 characteristics of this function. The possible values of the random variable are restricted to some open interval like this. And if you have 2 subintervals of it of equal length, the probability X takes on values in either is the same. Okay. So for instance, if this open interval is of length 10, and you take 2 subintervals that are of length 2, anywhere in that subinterval, the probability of it being in either subinterval of length 2 is the same. Okay. Okay, so those are 2 characteristics of this uniform probability density function. So this is example 5.10. Okay, a syrup is 99% pure maple syrup according to its label. If, in fact, the percentage of pure maple syrup in any bottle is a uniform random variable x with values ranging from 98.5 to 99.5, what is the probability that a bottle of this brand is A, less than 99% pure maple syrup? Okay, so example 5.10. A syrup is 99% pure maple syrup according to its label. If in fact the percentage of pure maple syrup in any bottle is a uniform random variable x with values ranging from 98.5 to 99.5, what is the probability that a bottle of this brand is less than 99% pure maple syrup? Okay, so what this means is this. Okay, so x, so what it's telling you is that the percentage of pure maple syrup in any bottle is a uniform random variable x with values ranging from 98.5 to 99.5. So I'm going to underline that. So the thing I underlined is telling you what the probability density function is for capital X. Okay? And so now let's just write down what that function is. So what is f of x here? So f of x is the probability density function of a uniform random variable x with values ranging from 98.5 to 99.5. So the probability is 1 for 98.5 less than x less than 99.5 and 0 elsewhere. Okay, so how did I get this PDF for this variable? Well, here, alpha is 98.5. Beta is 99.5, right? And from the definition above, f of x is equal to this. Right? So since f of x is equal to that, then what we want is f of x. So what is 1 over beta minus alpha? 1 over beta minus alpha is equal to 1 over 99.5 minus 98.5, and this is equal to 1 over 1, which is 1. Okay, so the denominator is 99.5 minus 98.5, which is 1 over 1, which is 1. Okay, so this function f of x is equal to 1 for x values between alpha and beta. So for x values between 98.5 and 99.5, f of x is 1, and it's 0 elsewhere. So you can see how we get this from that. Okay, so this f of x is our probability density function. Okay, so now that we found f of x, we can find probabilities of capital X being in a range of values. Okay, so for A, we want to know the probability that X is less than 99% pure maple syrup. So we want to know the probability that capital X is strictly less than 99. Okay. Okay. Right, because X, the percentage of pure maple syrup is the values of X, right? Percentage. So so X being less than 99 means we want the percentage of maple syrup to be less than 99. to want to know that probability, let me just maybe put the probability of less than 99% pure maple syrup is equal to that. And so then that's equal to the integral from negative infinity to 99 of our PDF of x dx. And so now this is equal to the integral from, now f of x is only non-zero between 98.5 and 99.5. So we can start at 98.5 and go to 99. And the function there is defined to be 1. And so we just have this integral. This is x evaluated from 98.5 to 99. So that's just 99 minus 98.5, which is equal to 0.5. All right, and so the probability of less than 99% pure maple syrup is 0.5. B, probability of more than 99.4% pure maple syrup is equal to the probability that capital X is strictly greater than 99.4. Okay, and so that is equal to the definite integral from, actually, this is 1 minus the probability of capital X being less or equal to 99.4. This is equal to 1 minus the definite integral from 98.5 to 99.4 of your PDF, which is x dx. And so this is equal to, 1 minus x, this is a 1. Right? So this is 1 minus x evaluated from 98.5 to 99.4. So this is 1 minus 99.4 minus 98.5. Okay, and then so this is equal to 1 minus, this is 0.9. So it's 1 minus 0.9, which is 0.1. Okay, so for B, the probability of more than 99.4% pure maple syrup is equal to the probability that capital X is greater than 99.4. That's also 1 minus the probability that X is less or equal to 99.4, which is 1 minus that, which is that. Okay. C, the probability of exactly 99% pure maple syrup is equal to the probability that capital X is equal to 99. And that's equal to 0. Because for a continuous random variable, the probability that your continuous random variable takes on any specific value is 0. It has to take on a range of values to have a positive probability. Okay, so 5.7.2 is on the exponential distribution. Okay, so a continuous random variable, capital X, has an exponential distribution and is called an exponential random variable if its PDF can be defined as follows. Okay, so definition. Definition 5.4. Let alpha, let theta be positive, be a constant. The function f of x is equal to one divided by theta, e to the negative x over theta, for x positive, and then this 0 elsewhere. That function is the exponential probability density function with parameter theta. Okay, so that is the exponential probability density function with parameter theta. Okay. Okay, so this PDF is called the exponential probability density function with parameter theta. It's of the form f of x is equal to 1 over theta, e to negative x over theta for x positive, 0 elsewhere where theta positive is constant. Okay, let's do an example. So example 5.11. The time interval in minutes between calls arriving is an exponential random variable with parameter theta. Equal to 0.5. Find the probability that A, there will be a wait of at least 1 minute between the first and second telephone calls arriving on a given day. Okay, so this is the example. Okay, this is our exponential probability density function with parameter theta, this thing, right? And so the time interval in minutes between calls arriving is an exponential variable with parameter theta equals 0.5. I'm going to underline that. That's telling you what you need to let x be. Okay, so let x equal time interval in minutes. Okay, between calls arriving. Okay, then the PDF of capital X is, well, we have the form from above, right? It's of this form, where theta positive is a constant, right? So what we want is our function to look like that. So if you want your function to look like that, then just plug in the value of theta. Theta is 0.5 here, right? So what you want is theta to equal 0.5. Okay, so theta equals 0.5. So you're just going to plug that in because it's positive. So you get 1 over 0.5 e raised the negative x divided by 0.5. This is for x positive. It's 0 elsewhere. Okay, so that's the PDF right here. It's of this form. Right? So your PDF of X, capital X is of this form. Okay, so now that you have the PDF, you can use it to find probabilities. Right? So in A, you're asked to find the probability of a weight, find a probability that there is a wait of at least 1 minute between the first and second telephone calls arriving on a given day. Okay, so a wait of at least 1 minute. X is the time interval between calls. So if you wait at least 1 minute, the word at least is also important. Okay? So you want the wait of at least 1 minute. X is the amount of time you wait between calls. So at least 1 minute means that you want this to be X greater or equal to 1. Okay, or it could be X greater than 1. Doesn't make a difference. X greater or equal to 1, I'm going to put. And so that's equal to the integral from 1 to infinity of f of x dx. And that's equal to the def integral, the integral from 1 to infinity of this PDF. Because when x is greater or equal to 1, x is positive. And so you're using that function there. That's dx. Okay, and so now you integrate that. And so if you're integrating with respect to x, then you find an antiderivative of this. 1 over 0.5 is 1 over 1/2. That's 2. And then the antiderivative of e to the negative x over 1/2, right? So here you have e raised to the negative x divided by 1/2. That's the same as times 2. That's the same as e to the negative 2x. Okay, e to negative x over 0.5 is the same as e to the negative 2x. Dividing by 1/2 is the same as multiplying by 2. So here we have the integral from 1 to infinity of e to the negative 2x, right? So then if we integrate from 1 to infinity of that, then what you get, you have e to the negative 2x dx. So when you integrate that, you let u equal to negative 2x. So du is equal to negative 2 dx. So by u substitution, you get that this integral here, this is not equal to 2. Okay. So you get this integral is equal to 2 times this. Right? Okay, so then it's 2 times this, but dividing by 1/2 is the same as multiplying by 2. So you have this integral here. Right? This becomes the 2 here. The x over 0.5 becomes the 2x, and then the negative sign in front. And then you integrate that. So you'd use this u substitution. So you need a negative 2 dx. Okay, so I have a 2 here. So I'm going to put this 2 here. I'm going to put a negative 1 here. And I'm going to put a negative 1 here. And so then this is equal to this step integral. So you have e to the negative 2x, which is u. Negative 2 dx is du. This is du. That's e to the u. And when x is 1, you get negative 2. And when x equals infinity, x at infinity is the same as u at negative infinity. So you get that integral there. Okay. Okay. Now this is also the same as the integral. If you switch it, you can change this from negative to, you can negate it, and so you get this thing, get negative infinity negative 2 of e to the u du. And when you calculate this kind of an integral, you take the limit as, let's say, m approaches negative infinity of the definite integral from capital M to 2 of e to the u du. So what's happening here is that when you calculate an improper integral, this means that you take the limit as the lower integrand approaches negative infinity, right? So that in calculus, that's how you calculate an improper integral. Okay, so this is stuff you've already done. This is the limit as capital M approaches negative infinity of that definite integral. So that's e to the u, an antiderivative, evaluated from m to 2. Okay, and so this is equal to then that same limit equals e squared minus e to the m. And now that limit, well, this is negative infinity. Okay. And then the limit of a constant is just that same constant. So this is e squared. Then minus the limit of e to the m as m approaches negative infinity is 0. It's e squared minus 0, which is e squared. Okay, so oh wait, okay, hold on. This is a negative, sorry, this is a negative 2 here. It's a negative 2. It's a negative 2, negative 2, negative 2, negative 2. Okay. So this problem, this integral is equal to e to negative 2. Okay, so I calculated it here for you. And so the final answer here is this is e to negative 2. As a decimal, that's equal to 0.1353. So probably x is greater than or equal to 1 is equal to 0.1353. And so I did the calculations below. Okay, and so here's the side work for the problem. And that's it. This explains how I get those, that equal sign over there. Okay, so for part B, there will be a wait of at least 1 minute between each of the first 5 telephone calls arriving on a given day. Okay, so we want to find that probability. We want to find the probability of a wait of at least 1 minute between each of the first 5 telephone calls. Okay, wait of at least 1 minute each of the first 5 telephone calls on a given day. Okay, so 2 things I want to illustrate, right? Point out. What's the probability of a wait of at least 1 minute? We calculate that already. That's 0.1353. Okay, between any 2 calls, the probability of a wait of at least 1 minute is e to negative 2, 0.1353. And B, you want to know what is the probability that happens in the first 5 telephone calls, that each of the first 5, there's a wait of at least 1 minute. Well, what you want is just the probability of a wait of at least 1 minute. You want to take that probability and you raise it to the 5th power. Okay, because waiting, the probability of waiting in the first interval for at least 1 minute is 0.1353, and then the probability of it happening 5 consecutive times is just multiplying those 5 probabilities. So it's 0.1353 to the 5th power. And then you do that, you get 0.00335. Okay. And then to add a little bit of work here, I'm going to write probability of a wait of at least 1 minute each of the first 5 calls is equal to that. Okay, so the probability of a wait of at least 1 minute each of the first 5 calls is the probability of a wait of at least 1 minute 5 times. That's this probability raised to the 5th power, which is that. Okay, so that's B. Okay, so random variables that satisfy either of the following 2 conditions are exponential random variables. Okay, so if either of these 2 things happen for your random variable, it is an exponential random variable. If the random variable, capital X sub t, that represents the total number of occurrences of the phenomenon from time 0 to any given time t is a Poisson random variable with parameter lambda t. Then the waiting time until the first occurrence is an exponential random variable with parameter theta is equal to 1 divided by lambda. Okay, so if you have a random variable x of t that represents the total number of occurrences of a phenomenon from time 0 to time t is a Poisson random variable with parameter lambda t, then the waiting time until the first occurrence is an exponential random variable with parameter theta equals 1 over lambda. Okay, so that's one way you can get an exponential random variable. The second way is if capital T is a non-negative random variable that is memoryless, meaning that the probability that capital T is strictly greater than S plus T, such that T is greater than little t, is equal to the probability capital T is strictly greater than capital S for all S comma T greater or equal to 0. And capital T is an exponential random variable. Okay, so these are all two situations where you have an exponential random variable. Let's do an example. This is example 5.12. So I'll stop for a minute if you want to write this down. Okay. Okay. Okay, so let's do the example. Example 5.12. Suppose the number of automobile accidents from time 0 to time t in minutes, in hours, along a segment of highway Z is a Poisson random variable, which I decided to capitalize, with parameter lambda t is equal to 1 over 15t. Okay. Furthermore, suppose there is an accident there at 10 a.m. Okay, so suppose the number of automobile accidents from time 0 to t in hours along a segment of highway Z is a Poisson random variable with parameter lambda t equals 1 over 15t. Furthermore, suppose there is an accident there at 10 a.m. Part A, find the probability that there will not be another accident along this segment of the highway for at least 24 hours. Okay, so let capital T equal time in hours until the next accident occurs along this segment of the highway. Okay, so here what we have is this situation over here. If the random variable x sub t that represents the total number of occurrences of a phenomenon from time 0 to any time t is a Poisson random variable parameter lambda t. That's so this part, that part is here. The number of automobile accidents is your phenomenon, right? And so the number of this phenomenon from 0 to t is a Poisson random variable with parameter lambda t, right? And so we want to find the probability there will not be another accident along this highway for at least 24 hours. So the waiting time until the first occurrence is your exponential random variable with that parameter. Okay, so let t equal time in hours until the next accident occurs along the segment of the highway. So t, then capital T is an exponential random variable with parameter. Well, it says here theta equals 1 over lambda. So it's theta equals 1 over lambda. Well, that's equal to 1 over, here lambda is 1 over 15. Lambda is 1 over 15, right? That's 1 over 15, which is 15. Okay. Okay, so you see that from 1 above. So then from 1 above, so from 1, t is an exponential random variable with that parameter. This is 1 right here, right? Okay. And so now we have theta. So then that means that we're now going to calculate our probability. The probability that there will not be an accident for at least 1 hour, at least 24 hours. And so that probability is equal to the probability that capital X is strictly greater than 24. Or greater than or equal to, they're both the same thing. And so now this is equal to the integral from 24 to infinity of our random variable of our PDF, right? Our PDF is a Poisson, is our exponential random variable. So it's 1 over lambda times e to the negative x divided by lambda sorry, it's theta. Let's say theta. Theta one over theta e to negative x over theta dx. And so then that's equal to, so you plug in the value of theta here. Right? So we have theta is 15. So we have from 24 to infinity of 1 over 15 e to the negative x over 15 dx. Okay, so we have 1/15. And so then you calculate this integral. So you do use substitution. And so it's actually the 1/15th. You want to keep the 1/15th in the integral. You want a negative inside and outside the integral. So let me express it this way. You have the -1. You have your integral from 24 to infinity of e to negative x divided by 15. This is your 15 here, 1/15th here dx. Yeah, okay, we have a negative. Okay. So I just multiplied the inside and outside by -1. And so the reason is because when you use substitution, right? We let u equal to negative x over 15. Then du is equal to negative 1/15th dx. That means that this integral, put it here, this integral is equal to this integral. Just multiplying the inside and outside by -1 and putting the 1/15th here. See that? And so now this is equal to the def integral. Now -1/15th dx, that's du. So this is e to the u, because that's u, du, that's the du. And then when x is 24, this is negative 24 over 15. And then when x goes to infinity, this is going to be negative infinity. Okay, and so then you switch the limits of integration, and it's negated, so the -1 goes away, and you get negative infinity to negative 24 over 15 e to the u du. Okay, and then this is equal to the limits as capital M approaches negative infinity of the def integral from M to negative 24 over 15 e to the u du. And then this is equal to this limit. Just write it again. Okay, this is equal to this limit times this integral. So I'm going to calculate this integral, and it's e to the u evaluated from m to negative 24 over 15. So you evaluate that, and you get the limit of e to the negative 24 over 15 minus e to the capital M. And so you take the limit as m approaches negative infinity, that goes to 0. So you just get e to the negative 24 over 15 minus 0. And that's equal to e to the negative 24 over 15. Okay, and so that def integral is equal to e to the negative 24 over 15. So this is from most of the side work for the problem. Okay, so this is outlining all the steps of calculating this def integral. So you just use substitution. That means by use substitution, you get this is equal to this, and then we use substitution, and we get this. And so we get this is equal to that, and as a decimal, this is equal to 0.20. Okay, so I'm adding in the calculations for calculating the definite integral here. Okay. B, find the probability that there will be another accident on the same day. Okay, so worded differently, this is the probability that the next accident happens in at most 24 hours. Right? If another accident happens on the same day, then you can kind of be ambiguous, because you could say, well, what if it's like 5 in the afternoon and it's like in the same day? Could mean it's not 24 hours later, right? But on the same day means within 24 hours, okay? In at most 24 hours. So what we want is the probability that X, the waiting time, is at most 24 for hours. And so this is equal to definite integral from 0 to 24 of our PDF, which is 1/15 e to the negative x divided by negative x over 15 dx. And so if you calculate this, then so actually let's not forget all that. Just think about this. It's 1 minus the probability that x is greater than 24. Right? And so we found this probability over here. It's this value, right? Probably that x is greater than 24 is that probability. So probably it's at most 24 is 1 minus the probability it's greater than 24. 1 minus that probability. And so that's equal to that's equal to 0.7981. Right, and so then that's B. Let's do another example. So this is example 5.13. Suppose an electrical system is maintained very well. So it makes sense to assume that the system will not fail for at least S plus T hours, given it has not failed for at least T hours. Okay, so suppose an electrical system is maintained very well. So it makes sense to assume the system will not fail for at least S plus T hours. Given it has not failed for at least T hours, is the same as the chances it will not fail for at least S hours. Also, suppose the probability it will not fail for at least ten hours is 0.99. 99%. Find the probability it will not fail for at least 100 hours. Okay, so I'll read this again. This is weird. Suppose that an electrical system is maintained very well. So it makes sense to assume that the system will not fail for at least S plus T hours. Given it has not failed for at least T hours, is the same as the chances it will not fail for at least S hours. So what you're assuming is that the system will not fail for at least S plus T hours is the same as the chances it will not fail for at least S hours. Okay. Also, suppose the probability it will not fail for at least 10 hours is 0.99. Find the probability it will not fail for at least 10 hours. Okay. So what I'm going to do is, as a solution, I'm going to let capital T equal to the time in hours until failure in the system. Okay, so let capital T equal the time in hours until failure in the system. Now let's look at this weird thing here. If capital T is a non-negative random variable, so here, time in hours until failure in the system, T is non-negative, right? Capital T is non-negative. Start with the easy one. This is good, right? So the hours until failure is non-negative. Here. And so if T has to be non-negative, which it is, and it has to be memoryless, meaning this equation is true. And then the conclusion after that would be T is an exponential random variable. So what we want is this. Okay, so we want is this. So let's look at this problem again, see if this happens. It does. Okay, so so it says we're assuming that the system so the chances of the system will not fail for at least S plus T hours, right? T, the time until failure, is greater than S plus T, given it has not failed for at least T hours, given that T is greater than little t, that probability is the same as equals to the chances it will not fail for at least S hours. Okay, I'm going to put a little s here. This is little s, little t. Okay, let me fix that. Okay, t greater than little s, little t, greater than 0. Okay, so the chances the system will not fail for at least S plus T hours, given that it has not failed for at least T hours, is the same as the probability that it will not fail for at least S hours. Okay, the probability that it will not fail for at least S plus T hours, given that it has not failed for at least T, is the same as the probability that will not fail for at least S. Okay, so this is memoryless. Good. So T is memoryless. This is also good. Okay, and so the conclusion of 2, these are random variables that satisfy either of the 2 conditions are exponential random variables. So since T is non-negative and it's memoryless, then T is an exponential random variable. And so by 2 earlier, t is an exponential random variable. Okay, so t is an exponential random variable. To find theta, we see that following. So we know that 0.99 is the probability that x is that xt is greater or equal to 10. Okay. And so that's from here. Find the probability it would not fail for at least 100 hours. Right? But before that, suppose the probability will not fail for at least 10 hours is 0.99. That's given to us, right? So the probability will not fail, the time in hours until failure is at least 10 is 0.99. And so from that, we get an expression for this probability, which we have equal to 0.99. Okay, and then we move forward. So it's the depth interval from 10 to infinity, 1 over theta, e to negative x over theta dx, and that's equal to e to the, you do the calculations of the integral, it's e to the negative 10 over theta. Okay, so when you calculate this integral, this improper integral, you get this using U substitution. And so what that tells you is that 0.99 is equal to that expression. Okay, and so since they're equal, take ln of both sides. ln of 0.99 is equal to ln of the right side, which is negative 10 over theta. Okay, and then you solve for theta. And so theta is equal to negative 10 over ln of 0.99. Okay, and then when you calculate that, that's equal to positive 994.99. Okay, ln of values less than 1 is negative. So this is actually negative in the denominator. So it's negative 10 divided by a negative value, and that's why this is positive. Okay, and so this means that the probability that the system will not fail for at least 100 hours is equal to the probability that xt, the waiting time, is greater than or equal to waiting time until failure. Probability of t greater than or equal to 100, and that's equal to f interval from 100 to infinity of 1 over theta e to negative x over theta dx. And we know what theta is because we found it here. It's this. So I'm going to plug in theta. So f integral from 100 to infinity, improper integral, 1 over 994.99 e to negative x divided by 994.99 dx. Okay, and then that's equal to calculating it. We'll calculate here. So if you calculate that, get e raised to the negative 100 over 994.99. That's equal to 0.904. Right, and so that's the probability that the system will not fail for at least 100 hours. So what we had to do first was recognize that our t we defined, the wait time in hours till failure, was an exponential random variable by 2, right? We had a non-negative. This is a non-negative random variable, which is memoryless. And so since t is non-negative and memoryless, 2 concludes that t is an exponential random variable. And what that means, what it means for t to be an exponential random variable is that its PDF is of this form. Okay, and so now that its PDF is of that form, you're given that the probability that if it takes at least 10 days, 10 hours, at least 10 hours, probably it will not fail for at least 10 hours is 0.99. And so you represent this probability as this using this integral. And so you know this expression equals 0.99, and you solve for theta. And now that you know theta, you know what the PDF is. Before you didn't know theta, right? You needed this equation to find theta. Now that you have theta, you have the PDF because you know it's an exponential random variable. And so, now that you have the PDF, you can calculate this probability to get the answer. Okay, so all of that was this example 5.13. Okay, and so I'm going to say one fact, and then we are done with today's lesson. If the waiting time between events of a specific kind is an exponential random variable with parameter theta, the number of events of this kind from time 0 to time t is a Poisson random variable with parameter lambda t. Which equals 1 over theta t. Okay, and so we're going to stop there, and then next time we'll continue. So there's no new homework for next class. Okay, so have a good night, and I will see you on Wednesday. Okay, you're welcome. Okay, so I believe I was recording this lesson. I was.